heck, I just talked about this on the last page. Here's the sum of the first 100 integers. So here's what he did. This was a teacher. Think about a teacher being hungover and not wanting to deal with the kids. Just said, go and add the first 100 numbers. So here's what he did. He lined 100 up forwards and he lined 100 up backwards, all the numbers, right? And he realized that when you add each one of those pairwise, you get 101 every single time. Well, what has he done? He's counted 101 100 times, right? Because there's 100 of these numbers. So it's 101 plus 100, so that's 101 times 100. But then he has counted 100 twice. He did it forwards and he did it backwards, so he had to divide by 2, and that's how he got the number right there. So he did 100 copies of 101, but that was counting it twice, so divided by 2 got the answer. And that's where that comes from right there, and he was quickly able to get the property. Just absolutely amazing how his mind worked. Put it forwards, put it backwards, and notice a pattern, okay? So what we want to do now is we want to evaluate the sum as I equals 1 to n of I plus 1 all over n squared. Well, if you notice here, and this says for n equals 1,000, so for n equals 1,000, if you think about this, this n squared is constant. The only variable that we have is I plus 1. So essentially, if we expanded this, if we looked at this expanded, what you would see here is you would see a 1 plus 1 over n squared plus 2 plus 1 over n squared plus 3 plus 1 over n squared, all the way to plus n plus 1 all over n squared. What you notice is every single one of those has an n squared in the denominator. And so what we could do is factor that n squared out. So what we're really looking at is we can pull, just like we do with derivatives and antiderivatives, you can pull any constants out in front. And remember, n here is a constant. I is the variable. I is the thing that changes. So the sum of I equals 1 to n of I plus 1 all over n squared is the exact same thing as 1 over n squared times the sum of I equals 1 to n of I plus 1. So we can pull that n squared out. Likewise with addition, we could also, same thing with the derivative rules and the antiderivative rules, and limit rules, you can separate addition. So what this really is 1 over n squared times the sum of I equals 1 to n of I plus the sum of I equals 1 to n of 1. So what are we able to do now? Now we're able to use those rules that we had on the previous page. We know that the sum from I equals 1 to n of I is, and this is given by that formula on the previous page, n times n plus 1 all over 2. We also know that a sum of a constant is that constant times n, or in this case it would be 1 times n, which is just n. So what do we really have? We have 1 over n times n plus 1 all over 2 plus n. That's what that series must be. Oh, sorry, that's an n squared out in front. I don't know why I messed that one up. So what do we have? Well, it looks like we could get a common denominator by multiplying this by 2 over 2. So that would be n squared plus n plus 2n. So what would that be? N squared plus 3n? All over 2, and that's times 1 over n squared. That's just getting a common denominator. And so this would be n squared plus 3n all over 2n squared. Well, I noticed that we have an n in common on top, so this would be n times n plus 3 all over 2n squared. I could simplify that n, and when I do that, I'd have a simplified version of n plus 3 all over 2n. So this would be the closed form formula for this. Regardless of what n is, it sums to that value of n plus 3 all over 2n. That is the closed form formula. Really, really cool, because now rather than summing 1,000 terms, all we have to do is plug in n equals 1,000. So in general, the answer is n plus 3 all over 2n, but let's look at it specifically at n equals 1,000. you would have 1,000 plus 3 over 2 times 1,000. And when we do that, we would get, I'm getting 0.5015. So that's what I'm getting there right there, 0.5015. So rather than adding up 1,000 terms, which would take forever, all we had to do was a little bit of math, a little bit of algebra, a substitution for these two rules that we know, I and a constant, and then we were able to come with the closed form formula and then just plug in the in. Well, let's start relating this back to what we saw in the first chapter we covered. And remember, the first chapter we covered was on limits. So the idea would be what happened if we made n bigger and bigger and bigger. And so what they did here is they took that closed form formula that we got. Let me go ahead and highlight that for you so you see what we're looking at. We got n plus 3 over 2n. And then they start plugging in all these different values for n getting larger and larger. Well, look what's happening to the actual mathematical values. It looks like as n gets bigger, the y value, not the y value, the summation value is getting closer and closer to 0.5 or 1/2. And that is the exact same thing as this right here. So rather than taking numbers and plugging it in as a chart, what they're doing is they're going to take the limit as n goes to infinity of our general closed form answer. And when you do that, what they did was they separated it. So they looked at it as, personally, I would have seen this as balanced because it's a fraction and you have an n on top and on bottom. So I would have done the ratio of the leading coefficients, which is 1 over 2, and you would have gotten your answer. But what they did was they separated it. They had n over 2n, which is 1/2, and then they had 3 over 2n, and that's fine. The limit of a constant is the constant, and the limit of 3 over 2n, remember this denominator would be getting huge, so the overall number would be approaching 0, so that's how they got 1/2. I would have just said it's balanced equals 1 over 2, or 1n over 2n, which equals 1/2. So they get the answer there. So limits, they do the limits using a chart, and they do the limits using the formal limit process. So what happens to this summation as n approaches infinity? It approaches a single value, and in fact it approaches the single value of 1/2.